All right, how's it going, everybody? Here we are for part two of our conclusion in chapter two here. We looked at a bunch of things in 2.3 through 2.7 yesterday. Fix that right there. I'm missing a decimal point. And today we're going to wrap that up. We're going to look at some of the other topics here that we didn't get to yesterday. I guess I kind of referred to these as the harder things yesterday. I don't even know if they're that much harder. I think I could call them maybe more time consuming, um, slightly. Even then, that's not necessarily the case here. But in any event, we're going to wrap up these sections here today that are all about our basic descriptive statistics that are associated with typical data sets. Again, like we talked yesterday, technically speaking, any data, any value that you compute based on a data set is a statistic. We are interested in statistics that are actually useful to us to help describe data. And so we saw last video that depending on what our data is like, certain statistics are more useful than others to be descriptors there. So today we're going to kind of continue on with this here. This will be our wrap up for chapter two, and next week we'll begin chapter three, which is all about probability, which is honestly one of my favorite topics here in this course. Aside from statistics, probability is intensely related to statistics here. Probability is one of my favorite things to talk about, so I'm definitely looking forward to chapter three. And gosh, before I get started here, I just feel obligated to document the fact that it is crazy outside right now, with the fires that are currently in Willits, I believe, outside my window here. I don't know how much this is visible on the screen there, but oh man, the sky, my dogs are freaking out, and my kid's just been sleeping all morning because he thinks it's nighttime, and it's crazy out there right now. I haven't not heard a helicopter since I woke up. So I hope that this fire is not too destructive for everybody here and the people that are south of us here in Humboldt. So crazy. We'll be watching the news for sure. So okay, now back to statistics. Uh, get a little closer here. There we go. Okay. So let's just kind of quickly remind ourselves all the conclusions that we landed on last class period here. Last class, we looked at computing a variety of what are generally referred to as simple statistics. It's not too much of a pain to compute or interpret some of these. There are thousands of other worthwhile statistics that are out there that are certainly less simple to compute and understand, that are still meaningful. We're just kind of looking at the basic computations associated with data sets here. So last video, we looked at things like mean, median, and mode. Those are our measures of center. We computed, not even computed, we recognized that identifying the minimum, the maximum, and consequently the range helps us understand the spread of the data, sort of. But I think that range is honestly one of our worst measures of spread. Um, Maybe I'll amend that statement. I think that alone range is a bad measure of spread, but I think that knowing the range of a data set is actually incredibly useful all the times that you understand what type of values your data could possibly take on, the minimum and the maximum there. So it is useful, but rarely useful as a standalone statistic. We looked at identifying some quartiles. I think an important thing for us to remember here is that for our quartiles, we typically denote these as Q1 and Q3, but don't forget that the median is Q2 because that is the location where 50% of the data is below and 50% of the data is above. A quartile is 25% of the data, and so quartile 1 is the location where 25% of the data has values less than that. Quartile 2 is the median, where 50% or half of the data have values below that. Quartile 3 is the third quartile, 75th percentile, where 75% of the data is below quartile 3. We defined the interquartile range, or IQR, to be Q3 minus Q1. It's the middle 50% of our data, and that's a really good measure of spread. It helps us get a sense of where our data is most centrally located. The interquartile range does not describe the outer 25% on the left and on the right, and that is often helpful in data sets where we might have outliers or some sort of heavy skew, because we don't necessarily want the skewed part or the outliers to have a big impact on how we really think about the data, possibly. And in those cases, then the interquartile range is a great descriptor of those data sets kind of trimming away maybe some data points that are not representative of the population overall. We also looked at computing standard deviation. Standard deviation is going to be a really important statistic for us this semester. We're going to mean and standard deviation are going to be by far our most used statistics this entire semester here. We did do a by hand standard deviation computation yesterday. In fact, we did two of them. And be aware, I probably will ask you to do one by hand, like on our first test, but it will also be with a small and simple data set, just like we did in the video yesterday. It's meaningful to know what the computation looks like, but for the most part, most of these things here, I am more worried about our ability to interpret and use these statistics meaningfully rather than simply compute them. Computing is for computers. People are supposed to be doing the thinking and the question asking here based on the statistics. So having access to your resources matters. It matters that you work to find ways to compute the values of interest to you, whether you're using Excel, whether we're using a TI calculator, or other resources that are out there. We use these statistics to then produce some displays of data. A 5-number summary is not a graph, but it is, I feel like a 5-number summary is like exactly living halfway between a statistic and a graph. 5-number summary is really 5 statistics combined. It is the minimum, Q1, the median, Q3, and the maximum. And it really gives us an idea of sort of the boundaries of our 0th, 25th, 50th, 75th, and 100th percentile. Technically speaking, I just spoke slightly statistically incorrectly there, since we should never refer to 0th percentiles or 100th percentiles, but those are the min and the max right there. So the 5-number summary is a good way of identifying the spread of our data only by looking at 5 numbers that represent the data set. The box plot is just a graph of a 5-number summary. That's all a box plot is. The box plot and the 5-number summary are essentially one and the same. One is just a visual representation, one is a numerical representation of exactly the same information. Box plots are also very good for helping us get a visual sense of the spread of the data. Histograms are a little bit different than the box plots there. Histograms are counting frequencies rather than of results rather than looking at groupings, lumping things into chunks of 25% at a time as the box plot does. So they do a slightly different job, but we can infer lots of similar information from them, such as the skew or symmetry associated with the data set. And that's exactly what I'm saying in my next paragraph here. These statistics and graphs were used to help us determine, we can identify things like, is our distribution skewed left or right, or is it maybe symmetric? What does the shape of our distribution look like? We're going to talk about that a little bit more here today, but we're going to see a bunch of our distribution shapes crop up in chapter 3 and chapter 4. I'm going to like soft introduce the idea of some distribution shapes today, but I'm going to try my best to leave a lot of the technical detail out of that. The other thing that these statistics and graphs helped us do is they helped us determine which measures of center and spread are most appropriate to describe a data set. What we saw yesterday is that in some data sets, it is better to use the mean better to use the mean as a measure of center, and in some data sets, it's better to use the median as our measure of center. What we concluded was that if the data are symmetrically distributed about the measure of center, if the stuff happening on the left is about the same as the stuff that's happening on the right, in that case, or I should say, in general, we always hope to use the mean. The mean is by far going to be our most convenient measure of center to ever use. We always hope that the mean is our measure of center. It's always our first choice. However, if our data are not symmetrically distributed, then that means that we're going to have a long tail on one of our sides, either left or right skew. There are probably going to be some outliers associated with that data set. And what we saw in our video yesterday was that outliers have a huge influence on the mean, whereas they have little to no influence on the median. Therefore, if we do have non-symmetric data, it's much better to describe the center of the data with the median, and then using the interquartile range as the measure of spread. So the other thing to know here is that the skewness will help determine for us whether or not mean or median is appropriate. If we determine that the mean is appropriate because the data are symmetric, then that tells us we will also use standard deviation as our measure of spread, center and spread. Where is the data located? How spread out is it from that center? Alternatively, every time that you decide that the median is the more appropriate measure of center, you should always then use the interquartile range as your measure of spread. There end up being just some crazy interpretations that you can come up with if you try to interchange these, like talking about the median with standard deviations. You'll end up with statements that are going to give you things like things being 100 standard deviations above normal, or just, I don't know, some kind of weird things like that that are not helpfully descriptive to me. And so, in general, mean and standard deviation are always a pair, center and spread. Median and interquartile range are always a pair, center and spread. We are going to add on to that today shape. So, our goal ultimately is to describe the shape, center, and spread of a distribution. And if we know all three of those things, then we can make a ton of inferences, calculations, predictions associated with individuals from that population. So understanding shape, center, and spread of a distribution of data is, in a sense, one of the most important things that we do this entire semester. It's going to allow us to make every computation and every decision that we want to make this semester. Shape, center, and spread is our key here. So that's the stuff we did yesterday. My last kind of conclusion statements from yesterday. The preferences that we have for mean and median are based on the fact that the mean, we say that the mean is not a resistant measure. The mean can be heavily influenced by one single data point if that data point is far away from all the rest. The mean does a bad job of resisting the effects of outliers. It's heavily influenced by an outlier. The median is a resistant measure. It is not heavily influenced by, and I put in italics there, the value of a single data point. What we saw yesterday as I looked at those two incredibly simple data sets, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 50. The 50, the value is now 10 times larger than in the previous data set than when it was a 5, but that didn't affect our median whatsoever. The median doesn't really care about the actual value associated with the data point. It only cares about the size of that data point relative to the ones above it and below it. All we're asking is that bigger than that data point? And 50 is bigger than 4. The average cares that 50 is way bigger than 4. The median doesn't care that it's way bigger. The median just cares that it is bigger. Any number bigger than 4 would have the exact same effect on the median. If that value were 50 trillion, the median still wouldn't have changed. The mean would have been wildly changed, however. Right? So we want to make sure, again, that we are not allowing our statistics to be heavily influenced by one single data point or a small few number of data points in the data set. The purpose of computing a statistic is to try and get a snapshot of what the data collectively looks like. And so if we give too much influence to a couple outliers, then that's not really necessarily giving us the most representative description of our overall data set out there. So again, we always want to use the mean, but there's a couple things that can go wrong in a sense with using the mean. There's a couple of reasons why it's not a very good descriptor in certain cases. And so it matters that we always stop to consider the shape of the distribution of our data before we attempt to compute statistics and use those to describe the data set. So what are we doing here today? As promised yesterday, today we are going to look at estimating the mean from a frequency table, computing and locating percentiles, which is a little bit more technical than quartiles, but not really too much here. We're going to compute and interpret a few z-scores, which we have not yet defined, but which are going to be, man, you're going to compute at least 100 z-scores this semester, probably more than that. All of this will be coming starting in chapter 5 right there with that stuff. So computing and interpreting these z-scores is fortunately relatively easy, and it's incredibly practical. This helps us make comparisons across data sets that are not necessarily describing the same things. We're going to sort of look a little bit at typical shapes of distributions of data, but as I said a minute ago, I'm going to try to avoid getting into that too much because we're going to talk about that in more detail later. I don't want to get into that detail now since the details about those distributions are not the content of this chapter right here, but I want us to kind of have a sense of like what we might expect to see. And finally, we're going to pop over to look at some things on the internet here, a very special example of some misleading statistics. A really smart dude got really frustrated with his students. I think I over-exaggerated yesterday. I think I said this was like 100 years ago. It was about 50 years ago. I saw on Wikipedia 1973 is when this dude decided to come up with these data sets to help reinforce to people that we don't want to rely too heavily on the statistics that we compute to analyze data, that it always matters, no matter what, that you actually look at your data, that you actually graph your data to help you make the appropriate interpretations about what you're supposed to see from the data. So this is like one of those things where you see this snapshot once and you're like, oh, that all makes sense to me now. So the special examples of the misleading statistics is it's kind of like a perfect thing from a professor's standpoint right there. I'm like, man, like that nailed it. It's like all this. It's a great example of a very important concept all wrapped up in one tight little package. So we'll see that at the very end here. So let's get started. These first two we're going to do together. We're going to estimate the mean from a frequency table, and we're going to talk about some percentiles also associated with the same frequency table here. So here's our first example for the day. I've made a frequency table here. A professor polls their students to determine the number of hours that each student spends working on homework each week across all of their classes. The students' responses are found in the following frequency table, and so it appears that this professor has already lumped up these things into categories here. It, all of our responses are 0 to 2 hours, 2 to 4, 4 to 6, 6 to 8, 8 to 10 hours. So we can see that there are the number of students' responses here, the frequency of response associated with this data class that's associated over here. I don't know if this is a word that I've been using, but this is each of these is one data class. It's a group of values that our data is getting lumped into. It's certainly possible, it seems to me, that a student could have responded things rather than 0, 1, or 2, like 3 or 4, or excuse me, like could have given responses like a 1 hour per week, 3 hours per week. And so these are getting lumped into these 1.5 hours per week, 5.5 hours per week. So we're putting these into intervals right here. What we would like to do with this frequency table is estimate an average amount of time that the students in the class spend on homework per week. And then we'll ask 2 questions associated with percentiles as well with this data here. So let's go ahead and do this here. So one of the things that we want to do, so let's talk about our average amount of time the students spend per week. What we are in a sense interested in is finding one statistic. On average, how much time does the average student spend on homework in this class? First things first, just by eyeballing this data set right here, it looks like this data set is going to land us somewhat relatively close to 12, the center right here. I mean, I see the 12 responses in the middle. I see that my next categories outside of it have relatively similar number of responses, 7 and 6. And then I see that the data class one step further away from 12 also have pretty similar response values right there. My first observation that I want to make about this frequency table is that this data does seem relatively symmetrically centered around the 4 to 6 hours spent right here. And I can see that by looking at the data values that I see in the frequency table right here. So I'm expecting, just by eyeballing this, that I should be expecting some answer that's going to land me somewhere in this ballpark right here as far as our overall class average number of average hours per week spent on homework here. So what we want to do is we want to actually make a computation, though, to make this estimate happen. So here's the thing that I'm thinking to myself. I don't know what the students actually responded if they landed within any of these given intervals, right? What a student could have responded at any one point in time is they could have said, I spend on average 3 hours and 16 minutes per week on homework. If they would have responded 3 hours and 16 minutes per week, then I'm going to throw them into the 2 to 4 hour category right there, certainly, right? What the issue is that we truly don't know what the students actually reported. It could have been that they were all reporting whole numbers. Maybe they all reported things accurate to 15-minute intervals, stuff like that. That much is unclear. This data has already been categorized for us by the researcher. We are doing our best to re-extract the individual raw data from this. And so we're going to make the best estimates that we can. And so here's the way that I think about this. If I'm thinking, for example, about the 0 to 2 data class right here, then what I'm thinking to myself is all the 3 people that landed in this data class from 0 to 2, I truly don't know what they actually reported as their average number of hours spent on homework per week was. I know that they reported something more than 0 and less than 2, or allegedly less than 2 in a sense, because perhaps the 2 is maybe our cutoff right here. Maybe, and by the way, maybe we can assume in this case right here that this goes from a lower bound of 0 up to, but not including 2. This begins at 2 and goes up to, but not including 4. Or maybe we should make that interpretation right here, but it's not really going to matter. The point is, what I need to do is make a guess as to what the average response time is that each of these three students gave right here. And the problem is that we have no additional information. Right? It could have been that all three of those students said 15 minutes per week. It could be that all three of those students said an hour and 55 minutes per week. We aren't sure about that. And so the thing that I kind of like to think is I don't have any reason to think that any one value in the 0 to 2 range is any more likely for one of those students to report than any other value. And so therefore it seems to me like the best representative number of hours that's associated with this week right here would be that I would expect that each of these three students, it should probably be the case that their three responses were on average all about 1 hour, because 1 hour is the center of my data class, the midpoint of my data class. So what I'm going to think to myself right here is I'm going to kind of add another column over here. And I'm going to say, I'm not drawn. Why am I not drawn? Okay, we're drawn. Okay, all right. So I'm going to say midpoint of data class. And what I'm going to identify is what value falls in the middle of all of these. The point is, I don't necessarily think that any of these values should be necessarily towards one end or towards the other end more than anything else. And so the best thing I can do here, since I think that everything is equally likely, is pick the value that's in the middle to make that as my estimate for what their actual responses were. And so here, these are all very simple. The midpoint of the data class from 0 to 2 is 1 hour. From 2 to 4 would be 3 hours. 4 to 6 is 5 hours. 6 to 7, the midpoint is 7 hours. 8 to 10, the midpoint is 9 hours. The reason that I'm making these estimates here again is because for the 12 students that responded that they could work on homework from 4 to 6 hours per week, it's unclear to me what number of minutes and hours they actually reported. And since I don't have a reason to think that any one is any more likely than any other, I'm assuming that all number of values between 4 hours and 6 hours are equally likely. And therefore, across the 12 students, it should be that on average, the 12 students that reported their work time between 4 and 6 hours, these 12 students probably have an average work time of around 5 hours per week, because that is the center, the midpoint of that given data class that's right there. So now what we want to do is actually use these midpoints to help us estimate this average right here. So let me get this out of the way here. So what we know about an average is that we would like to add up a certain number of quantities and then divide by the total number of quantities that we have seen. So one of the things that I should probably always do when I see a frequency table is stop and ask myself, what's even the sample size right here? And I can see that 3 and 7 makes 10, 6 and 2 is 8, 12 and 8 is 20, and 10 makes 30. So just adding those guys up, it looks like there are 30 students in this class. So I know I have a sample size of 30. So if I'm going to go ahead and compute my average here, then I know I'm going to add up a bunch of terms on top. And I know I'm going to divide by the grand total 30 representative students that are all contained here. Rather than adding 30 numbers up here, I know that a bunch of these numbers are going to be the same. What I'm seeing here is I am making the estimate that 3 students spend about 1 hour per week on homework. Katie, what's going on? Uh, how frozen is it, Katie? I know that I occasionally get some drop frames here, but my video ends up good. I saw. Glad to have you in here, Katie, for some stats. I'll be doing some calc this afternoon. Uh, Hopefully we're not too frozen here. Oh, really? For a whole minute? Seriously? Is my internet like not working? I'm actually getting no warnings about my drop frames, which I actually normally do. I'm all in the green right now. It says my stream quality is good, is what it's oh, there we go. There's my first one. Drop frames detected. Help you with your linear algebra? Yeah, I do. Just after this video here. So I'm gonna hope that this is picking back up. That seems strange. Maybe I'll blame it on your internet there, Katie. It's claiming that my my stuff is looking good right now. So I'm going to move forward, I guess. Uh, okay, good. There we go. Hey, there we go. Thank you, all you people, for letting me know that I'm not crazy. Yeah, there we go, Katie. Trying to make me feel bad. There you go. Uh huh. Uh huh. Uh huh. I see what you're doing. Coming in here, sabotaging. All right. So estimate this. You're good. You're good. I'd rather have you here than not. Uh, so computing our average here, we want to add up in a sense 30 values, but man, Katie, you could stay. Come on. But what I don't want to do is literally add 30 numbers here, right? I'm going to make this estimate here that the three people spent 1 hour per week. Well, I can accumulate all three of their responses here. There's three ones. That's the same thing as me writing 1 plus 1 plus 1 to represent those three students there. I can walk on down the line doing a similar thing here. I am estimating that 7 students spent approximately 3 hours each per week working on homework. So I'm going to add 7 copies of 3 hours per week right there. And we can keep walking down the line. And again, notice this is the same thing. This right here is the same as me just writing plus 3 plus 3 plus 3 plus 3 plus 3 plus 3 plus 3, right? 7 plus 3s. I'm not going to write all that. I'm going to just represent this as a simple multiplication. We have 12 students that we're estimating at 5 hours per week. So that's 12 students at 5 hours per week as their contribution to the average. We've got 6 students that are at 7 hours per week. And we have 2 students that we're estimating at 9 hours per week. You should notice that 3 plus 7 plus 12 plus 6 plus 2 is exactly the 30 total things that we're adding up right there. So we are adding 30 objects and dividing by 30. We just wrote it as 5 multiplications because we had 5 data classes. This is just us trying to make a simpler setup for ourselves right here. So I can go ahead and I can actually compute this average now. It looks like we're going to get 3 plus, and I'll just do a little by hand math here and then go to my calculator to get the rest of it cleaned up for me. And I'm going to throw this guy into my calculator here, and we will land at an estimate. And by the way, before I do this, I want to kind of point out to you guys like a general life thing that you should pretty much always do forever, which is I think that a really smart thing to always do every time you're computing something is to guess first. And you should never just stop at a guess. You should move on to your computation. But every time you make a guess and then your answer is very close to that guess, that helps you validate that you know that you're visualizing the situation correctly. Or if you make a guess and your answer is wildly far off from the guess, then you can either judge that you must have done something wrong or that you need to kind of update how you're thinking about this problem because your estimates aren't very good. Or we're going to find ourselves in situations where it's just really hard to make good guesses. But remember that at the beginning of this, we kind of looked at our frequency table here and said, hey, it looks like our data points are certainly centered around this grouping right here. Therefore, I'm expecting my response to be somewhere in this 4 to 6 range. I want to remember that that's my guess. I'm guessing I'm going to get a number between 4 and 6 when I do this computation over here. That's going to help me feel good about my answer right here, kind of help validate what I'm doing. So 3 plus 21 plus 60. My gosh, it's so dark in here that I can't even see my calculator. I have lights on, which I normally never do. Okay, I'm getting 144, and I'm dividing that by 30. So 144, dividing that by 30, and I am seeing 4.8 is my answer. That is very validating to me because 4.8 is very near to the center of that data class as we estimated. One thing I think that is kind of worth noting here is it is slightly below the midpoint of that data class, and that makes sense to me because we had a couple more data points below the middle than we had above down here. So this to me completely agrees with what my sort of intuition guess was right there. So we've computed an average based on a frequency table. And the point was here is that all of these responses weren't just a number. So it was important that we said, listen, I don't know what they actually reported if they fell into the data class 2 to 4. My best guess would be 3 because that's in the middle. So we came up with the midpoints of our data class, used the midpoints as the estimate actual value for the data class, and we multiplied the number of responses, the number of frequencies with that estimate, the midpoint of the data class, and that collected for us the 30 data points up here. So again, 3, 7, 12, 6, and 2, those are the 30 data points being added up, divided by 30, we computed an average right there. So for our average out of a frequency table, particularly when we are given our data classes as ranges. Our first step should be to compute the midpoint of each of those ranges. Our second step is to multiply all of the midpoints by all of their frequencies, add them all up, divide by the total sample size, and we'll end up with our average right there. So not too bad. This is still just computing an average. We just needed to do a little bit of work to do things like say, I needed to find my sample size of 30. I needed to find my midpoints out here. But once we got the midpoints and the sample size, computing this average hopefully looks a lot to you like the averages we computed yesterday. So what other questions do we want to ask here? Well, let's ask a couple of percentile questions here as well. What data, or determine the data class associated with the 30th percentile. So the really important thing to do here is to just know what our definition of percentiles are. If I say that something is in the 30th percentile, then what I mean is 30% of the data points should be less than that number, and 70% of the data points should be above that number. And let me just technically modify that statement I just made. 30% of the data points should be equal to or less than that number, and 70% should be equal to or greater than that number. They can be the same as well. So if I want to find the data class that is associated with the 30th percentile, then what I know is 30% of the n equals 30 data points are below. So what I can do is I can just find how many data points have I surpassed then. In this case, I am going to compute my 30% as a decimal. There's 30% times the sample size of 30. And when I do this computation, I know that 3 times 3 is 9. And with our decimal place, right, or 3 times 3 is 9. This is 30 times 0.3. I get an extra 0 from this, but I have an extra decimal place here. If we do this computation, we're just going to get 9. So what this says to me is the data class that's associated with the 30th percentile should be at the location where we are at the 9th data point in our ordered set right here. And so if I come up to my frequency table, I can see that we've accumulated 3 by this point, and we've accumulated 10 total students by this point right here. Therefore, it must be that this data class, 2 to 4, is the one that contains the 9th data point, or the 30th percentile data point. So to find the data class associated with a certain percentile, all we have to do is multiply the associated percentage times the sample size. My one stupid professor mistake right here is, in general, don't get confused with these. Those both were just 30s by total coincidence right there. I should have picked a different value. We obviously could right here. We could find the 40th percentile. Maybe we'll just do that. So this is going to be in the 2 to 4 data class. Maybe if we did the 60th percentile, then we would say 60% of our 30 data points. If we do this computation, we'll get 18. So now we're going to go up to our table and say, well, where did we get our 18th data point at? Notice here, this is like our cumulative frequency right here. We've accumulated 3 by our first data class. We've accumulated a total of 10 by the time we got to our second. We've accumulated a total of 22 by the time we've gotten to our third data class. So it appears that the 18th data entry is certainly going to be contained within the 4 to 6 data class. That's right there. All right, so these ones are pretty easy right here, that we can just multiply the percentile as a decimal times the sample size, and that will say, if you're looking for the 30th percentile, that essentially what you're looking for is the 9th data point from low to high. The 9th data point from low to high, because the 10th data point went all the way up to the 2 to 4, the 9th must have also been contained within that 2 to 4 range. That's right there. Alternatively, we can go the other direction with this one. What percentile is associated with studying exactly 8 hours per week? If I'm going to, sorry, I'm kind of scrolling away from that. What percentile is associated with studying exactly 8 hours per week? Now, one of the things that's important for me to even be able to do this problem right here, this is not even a question that I can directly answer exactly unless in this case I was given a boundary of one of our data classes right here. So this exactly 8 hours per week you can see is the boundary between these two data classes right here. So what I'm seeing here to fill out the rest of my cumulative column over here is it looks like we accumulated 28 and then all 30 of our data points by the final data class right here. So what I'm seeing here is if we are interested in the percentile associated with studying for exactly 8 hours per week, then 8 hours per week of studying, we are estimating that 28 students do less than that, and we are estimating that 2 students do more than that. Therefore, I can determine what percentile based on the fact that 28 out of 30 students are below 8 hours per week. So I'm going to say here from cumulative frequencies, "28 out of 30 students study less than or equal to 30 or 8 hours per week." So all I've got to do is just compute this as a decimal. 28 over 30. If I go to my calculator and I ask my calculator what's 28 divided by 30, and that's going to give me, I'm getting out of my calculator here, I'm getting 90 or 0.9333 repeating. Importantly, for percentiles, know that we never actually give a decimal ever for when we're talking percentiles. We never talk about the 92.6th percentile. It's always a whole number. So in this case, I am going to round to the nearest whole number and convert to a percent. And so here I would say that 8 hours per week would put this student in the 93rd percentile. So when we are hunting for a percentile associated with a data response, the question is what fraction of the responses were at or below that value? We then just compute the decimal that's associated with that, move the decimal over 2 slots, and we're landing at our percentile value that's right there. All right? So for these percentiles, really our important thing is to understand that percentiles are percentages that we can convert into decimals and use to do a little bit of multiplication here, find out where we're going to land with either the data classes that we belong in or the percentile associated with a certain type of response here. Right? So these aren't too bad right here. And I think that, again, the things that help for me is things like identify your sample size, identify your cumulative frequency column, identify the midpoints of your data class. Identifying some extra information that's associated with these frequency tables is usually a very helpful thing to do to help give you a better sense of things. Again, it's always useful also to make guesses. I probably should have made guesses on those second two since I just yelled at you about it. But do things like look at your frequencies and say, these seem pretty symmetrically distributed. I guess that the middle is going to be about where the average is, and 4 to 6. And oh, what do you know? We got 4.8. And so coming up with these estimates beforehand, it's really good for you to like validate yourself and say, I guessed that and that's what I got. And then you can feel good about your answers. Because a lot of the things in this class, I know that a lot of the things that students feel in this class, they do some computation and they're like, is that right? I don't know. And that's something that we hope to like kind of work through here in a sense. We want to develop intuition about being able to make guesses so that we feel good about our answers here. A little bit easier with averages, going to be a little bit tougher later with some other probabilities that we'll be computing. So what do we got next? Oh, next is our softest topic of the day in a sense, our typical distribution shapes. Uh-oh, now I did it. Okay. So I'm going to draw some shapes right here. And what I wanted to do is not try and take this too technically here, but there's a couple words that I think are worthwhile to kind of throw out to you here. So that we can kind of, just so that we have some common language that we're using to describe some of these things. There's a lot of different shapes that we can end up seeing our histograms take on. As we saw with our frequency polygons or frequency curves, it's a lot more common for us to represent our histograms as smooth curves over the tops of the bars rather than literally the bars themselves. So I'm going to start not with our symmetric things. So skewed left data is data where we are seeing a histogram that has a tail to the left. So in this case, I might see some data that has a histogram maybe looking like this guy here, and maybe there's some responses here, and maybe some stuff here. But then maybe we actually get like the meat of our data is actually going to be hanging out more to the right. This to me would be a skewed left data set because a majority of the data is hanging out right here. But there was a long tail out to the beginning. It seems possible that we're going to get lots of small responses, but for the majority, we get large responses out here. I want you to be picturing this instead, however, as a curve. I think this is like better represented in a sense by like some shape that looks like this right here. That's a pretty rough sketch right there, but the point is this is what I'm talking about, the shape of the distribution. We have a majority of the data located somewhere, but a long tail of the data is heading to the left. So whenever we talk about skew left and skew right, we're talking about the direction that the tail is traveling in. So for skew right, I'll draw a very slightly different picture for this one in a sense, aside from the fact that it's just going to be flipped left to right. The other thing that I'm doing here is you should notice that these curves that I've been drawing kind of, they're more like a hill. They have a top and a bottom. But it's certainly possible that we could just have a distribution that in a sense doesn't even really have sort of like a left chunk, right? And it's not like this doesn't have a left chunk, but I think you can kind of see the difference in what I'm saying right here. And this data right here, this is what I might call an exponential distribution. If you're an algebra student, you should see that this looks sort of like an exponential curve right here. And this would be skewed right because it has a long right tail, although a majority of the data is packed up around the x-axis over there. So this would be a right-tailed distribution or a skewed right distribution. Remember that we said in both of these situations, it would be more appropriate for us to use the median as the measure of center because in both of these cases, these values that are very far away from the center of the data are going to end up having a much bigger impact than we believe that they deserve, right? It's kind of like give equal representation to all of your data points. When you have outliers, those don't end up contributing equally to the values towards the center. So these are some of the ones that we've kind of seen before. So what are some of the other things that we should expect to see this semester? Well, what if we're not skewed left or right? What types of symmetric distributions can we see? Well, there's actually kind of a lot of these. In the same way, notice here that like these two are not really just like flipped versions of each other, right? I'm trying to give some other examples here without getting too technical about any of the details about these here. But I do think it's important that we identify a couple different ways that we could end up having some symmetry here. I think that the most typical thing to see for a symmetric distribution, the thing that we are going to see the most this semester, is what is commonly referred to as a bell-shaped curve. Now, notice that this distribution is not perfectly symmetric. It is not exactly the same left and right, but you should expect in statistics for nothing to ever work out to be perfectly exact, right? So if I look at this and I say to you, is this perfectly symmetric? You should say no, but I will never ask you that question because it's never meaningful. I will ask you, does the distribution look approximately symmetric? And you're going to look at that and say, absolutely yes. And even if it's got a little bit extra, if there's like one guy out there, that's not quite enough for to ruin me calling this guy symmetric right here, right? What we should expect to see for a distribution curve that's associated with this is a nice bell-shaped curve. And okay, that one got a little bit low relative to its histogram partner right there. But the point is, bell-shaped curve, the normal distribution is going to be by far our most used distribution over the course of this semester. So this symmetric distribution that is a bell-shaped curve, it turns out that a ton of things in the world are symmetrically distributed with a bell-shaped curve. And the question you should be asking is, why is that the most common distribution of values from populations? It comes up excessively in biology. Most things that are biological end up being distributed. The data are distributed normally according to a bell-shaped curve here. And there's a very good reason for that we'll be discussing at the beginning of chapter 4. We just need a little bit of our probability stuff in chapter 3 to get there. Now, my question for you is it possible for us to have a symmetric data set that's not a bell-shaped curve? And there's two very good examples of this. One we sort of talked about earlier. Another one is not one that we've talked about before, but that I want to throw out to you as a reasonable thing that might happen. So still under the symmetric heading, I'm going to draw another symmetric histogram right here. So in this case right here, this distribution sort of looks symmetric in the sense that there is a line that I could draw over which the left and right halves seem approximately equal to each other. This absolutely does have symmetry. And when we say symmetry, we mean left-right symmetry. But obviously, what you can see is that this is not the same as our previous histogram right here. In fact, somewhat concerning thing about this is that if I were to compute an average associated with this data set, the average would probably be about where this line of symmetry is right here, which is kind of unfortunate because that doesn't really describe this chunk of data or this chunk of data. Right? So if I were to draw a distribution curve for this, it's just sort of the curve. That's the same thing as the histogram there, right? It's going to be, my curve drawing skills are not great, but something like that. There's my approximate curve. And I want to give some words to these right now. The problem with this the problem with this data set, I don't want to say there's a problem with this data right here. The difficulty in describing this data set is that the average is in a sense a really poor descriptor of the data because the average is actually a very uncommon thing to experience. The most common things to experience would be these guys right here. Those two most frequent responses. And if you remember what measure of center we defined to be about the most frequent response, that was our mode, right? So here you should notice in this distribution that is symmetric, it looks like our mean, our median, and our mode are all in the same place right here. So here our mean is approximately equal to the median, is approximately equal to the mode. Right? Those are all going to be about the same since everything is symmetrically distributed. Here, I would refer to this, and I usually don't go out of my way to refer to it this way, but I would refer to this as a unimodal symmetric graph. And what that means to me is that there is one mode. That is making a distinction between this bimodal distribution right there, because it looks like two modes. There are two things that are really very likely out there. And now, I want to kind of back off again 1 second on this and say, if you're looking super carefully at my histograms, technically speaking, this is the mode of the data set. This one's technically a little bit taller than this one right here. But when we have two completely distinct peaks from each other on a histogram, I do think it's basically worth it to say that each of the peaks is representative of one of the modes of the data set, even if they are not of equal heights out there. Even if one of them is more common than the other, it's typically, I think it's smart to think of the mode not just as the most common data point, but maybe as what are all of the data classes that are resulting in a peak in our distributions graph right there. If we have a whole curve up and down again, then the top of that one should be a representative of a mode. So we would refer to these different symmetric graphs as unimodal and bimodal. This bimodal graph probably seems a little bit weird, but I can tell you that I see bimodal graphs all the time. And when I see them is that it is very typical for test grades to look bimodal. It's very typically the situation in lots of classes where when I give a test, there are a group of students that are generally well prepared and that there are a group of students that are generally not well prepared. It is very often the case that I give tests and like there's a bunch of scores packed up around like 88% and then a bunch of scores packed up around like 62% or something like that. So bimodal is a very common thing to see in academia. So I'm just saying, probably seems a little bit weird, but I can tell you, I see like half of all the histograms I personally look at in my life are bimodal typically because most of the histograms I make are related to like my students' performance on things. And it's very common for there to be the students that did the work and the students that didn't. And so so I would say, and I mean, I literally describe that when I have conversations with other math professors and they say, hey, I knew you gave your first calculus test yesterday. How'd it go? Okay, well, if it was yesterday, I wouldn't have graded yet, but okay. I know you just graded your first calculus test, Tony. How'd it go? I will verbalize my response back to the other professors saying, it was pretty bimodal. That's exactly what I like literally say to other professors, at least other math professors that know what I'm talking about when I say that. But that's my descriptor to them of saying a bunch of students did good and then a bunch of students did bad. It wasn't like there was just a nice smooth spread out there of how people did. That kind of, in a sense, says to me there were two groupings of total behavior that were out there. So there is one more symmetric graph that I want to throw at you, and it's actually one that I referenced earlier that I didn't. I almost considered rearranging the order in which I was going to talk about things today for that purpose, but we'll go ahead and stick it in here now anyway. Another thing that could happen here is just something that's far less exciting, and maybe here's my good example for you, the one that we actually did. In fact, we've already seen this one this semester. What we know is that in all these distributions that we've looked at here, what we're seeing is that all of the events have different likelihoods of occurring. Out here, the most likely event is at the tall stick, the least likely events are down here at the shorter sticks. We can say that about all of these things. These are all ultimately representing to us the probability that this certain event will occur. The most likely event in this unimodal symmetric graph right here, the most likely event to occur is the one that's associated with the tallest stick, that therefore has the highest probability of occurring. Well, we've talked about a probability situation earlier this semester that was not associated with that. That was associated with everything having the exact same probability. You should think about rolling dice. When we roll dice, everything should have the exact same probability as any other thing. That's literally the purpose of dice, is to make it a equal chance across everything. So if I were to roll a die 100 times, for example, I would expect to see a histogram that maybe looks something like this. Essentially flat. And I'm intentionally not drawing it perfectly flat because, as I said, there are no situations in statistics in which things end up perfect. Right? We refer to this as a uniform distribution. Distribution of data. All outcomes are equally likely. If all outcomes are equally likely, then they should all have approximately equal height on their histogram. So my histogram is always representing data I've collected. Data always experiences variation, and so I intentionally am, not quite perfect heights right there, but man, these are all essentially the same. It would be ridiculous of you to be like, oh, it's clear that this one is more likely than the others. I mean, they're all very close to each other, right? So our uniform distributions are the easiest graphs. They're just straight lines. And in fact, I'm even going to put like a little dashed line right there to indicate that it just basically drops off. It's not like there's some like, oh, and then this event is less likely and less likely down to zero. There's none of that right there. You have an equally likely probability until like the probability of a 7 is 0 when you're rolling a 6-sided die, and it immediately drops to that 0 right there. The good news is going to be that calculating probabilities associated with uniform distributions is going to be crazy easy, because this shape of graph right here is going to be very simple to work with right there. So let me just come back up real quick and throw a name on this since I didn't. This is a normal distribution. Bell-shaped curve. The name of that formally is the normal distribution. I will do my best to always capitalize the N on normal to make sure that I'm indicating to you that I don't mean regular. I mean the formal definition of normal distribution, which is this particular bell-shaped curve. And just as a tiny technicality, I'll say to you right now, not every single curve that looks to you bell-shaped is actually following the normal distribution. And we will talk about that in detail. That comes up in chapter 5, I believe, either 4, 5, or 6. I think it's going to be chapter 5. Um, so the normal distribution and the uniform distribution are going to be by far the two that we're going to discuss the most this semester. But it's important to recognize that lots of things in the world are skewed left or right. There are things, so let me maybe say some things like this. Home prices are something that are often skewed right. What you should think to yourself is that most homes are all valued 100, 200, $300,000. That is a majority of homes. But what you know is that there are a couple homes, and man, I mean, as me being a non-true Californian, being in California, I just think about driving up and down the coast. Just think about how many 10 million plus dollar homes are within a mile of the coast in California. All of those would live like out here on my histogram, not even on my curve, on my like histogram, right? That tail would extend forever out there. And for that reason, Home prices, it's never really representative to talk about average home price. Median home price in an area is a much better representative because home prices are never symmetrically distributed. There's always more homes that cost less money than there are homes that cost tons of money. And further, I can say with that, San Francisco, last I read, San Francisco actually has the highest in the world average home price. That's a misleading statistic, though, because average is just a terrible descriptor of home prices. If you look at home prices, they're not symmetrically distributed, and so the average is a bad estimate. That's because there are so many crazy expensive houses in San Francisco that it drives the collective average up. San Francisco does not quite have the highest median home price in the world, although I think it is in the top 10. Um, so there's like one good example of like a potentially misleading thing. If anybody's ever trying to convince you about something because of an average home price in an area, then they are using the wrong statistic. There is essentially no place that has a symmetric distribution of home prices. There's always those crazy expensive houses, but it's like, can you build a house for $20,000? Like, how many $20,000 houses are there? Like, essentially none. It's really hard to do that. So most things are packed up around that 100 to 300,000 range, but then there's a long tail of all those crazy houses that you can certainly find on the California coast out here. So this is a good example of home price. This is an example of why we use the median always to talk about home prices rather than the average. And there's lots of things like that. I think in your my open math homework, there's a question about NHL salaries, and it's a very similar thing. Most professional athletes never make it beyond the first 2 or 3 years of their professional career. Only a very small handful do. Therefore, all of those rookies that have no experience and aren't a big name and have only been around for 2 or 3 years, they're making a small amount of money. But we know that there's a couple of superstars out there that are always making the real big bucks out there, right? It's always huge news when some athlete signs the next biggest contract of all time. There's only like one person ever doing that, but it drags the average out very, very, very far. So again, average professional sports salary would be a terrible statistic. It wouldn't tell me much. Median sports salary would be a much better descriptor because the distribution is guaranteed to be heavily skewed right. There's going to be a long right tail on home prices, on sports salaries, things like that. Okay, that's enough about shapes here. Let's talk z-scores. This will be our last computation stuff for the day, and then we'll look at some pictures on the internet and we'll call it a day here. So comparing non-like data. The whole thing that we want to do this semester is make decisions about whether something is different than what we thought it was. That's like one of our biggest goals for the semester here. When we compare two objects that are very similar, it's pretty easy, right? For example, if the average weight of a certain variety of apple is 100 grams, and if I find two apples that weigh 110 grams and 120 grams, it's pretty easy for me to say very confidently that the 120 gram apple is more rare than the 110 gram apple because its weight is further from the average than the 110 gram apple's weight is. My immediate back off on this statement is I would need to be certain that I didn't have a bimodal distribution, right? If I had a bimodal distribution, this was 100, this might be 110, and this might be 120, where the 120 is actually more likely. But I find it very, very hard to believe that fruit mass is going to be bimodal here. That sounds to me exactly like something, without looking at any data, I feel pretty confident in guessing that we should be seeing pretty much all fruit weights of every fruit that grows in the world is very likely going to, the weights are going to follow a normal distribution rather than something like this bimodal distribution. So that's kind of easy to do in a sense then. In a sense, if we're comparing two like objects, the one that's further from the average is probably the one that's more rare. However, if we're comparing two non-like objects, I'm using this apple and oranges thing, like this is, I don't know, this is like a colloquialism in English. It's like you're comparing apples to apples versus apples to oranges. Apples to oranges is a non-like comparison that you shouldn't be making. And the point here is, but what if I really wanted to compare apples to oranges, right? What if I selected one apple and one orange that both seem larger than normal to me? How can I determine which of them is the more unlikely one? Which one is less normal than the other? And here, by the way, normal is lowercase. I really do mean normal is just like regular in this sense right here. In this case, we need more information about how the weights of those fruits are distributed to help us make that judgment call right there, right? So if I handed you a pretty big apple and a pretty big orange, and I said, is it weirder how big that apple is? Or is it weirder how big that orange is? you'd need to know a lot about the grouping of apples and grouping of oranges from which they came, right? The population of apples grown that year and the population of oranges grown that year to help you make that judgment because we're not comparing two equal items. They follow two completely separate distributions. So let's talk about how we can compute this stuff. And in this, I'm going to throw a little bit of notation at you, kind of getting ahead of it. This is stuff that's actually going to come up in chapter 4, at the beginning of chapter 4, but we're going to, I don't know, it's not that crazy. I'm going to hit you with it right now. So a large part of the semester, as I told you a minute ago, is going to be spent working with the normal distribution, and that's going to describe data that produces histograms that are bell-shaped. More than just stating the center and spread of data, it's also important to know the shape of a distribution. It's exactly what we just talked about. So shape, center, spread. Those are like the three descriptors of a distribution of a data set collectively that I typically want to know about. Since we'll talk about the details of the normal distribution a lot coming up right now, I just want to give some notation for this. So what I might say is this. I might say in these cases here, no, sorry, let me walk through the example and then I'll state some notation for these. In general, we list our notation for these things as saying our variable of interest, which in this case might be the weight of an apple or the weight of an orange. I'll call it X for right now. Our notation looks like this. The little twiddle right there is saying is distributed according to the distribution. What distribution? The normal distribution, which we'll denote with a capital N. The normal distribution, since it's a symmetric distribution, it's best described by its average and standard deviation. And so we just put those things next to each other, comma separated inside some parentheses. So this says to me, if I pick out an apple, it's going to have some weight X. That weight X is going to follow a distribution that is normal, symmetric and bell-shaped, with an average, and we'll put a number there, and a standard deviation. We'll put a number there. Our typical notation for this will end up being X is distributed normally. These are the two Greek letters that are used for average and standard deviation. That is not a U, that is a mu with an, it's just like say the letter U, but then stick an M in front of it. Mu. MU is how it's written. So mu and sigma are the average and the standard deviation. So this says if I grab an apple, I know that the probability of its size is going to be determined by a normal distribution with an average and a standard deviation given by mu and sigma. So I'm going to give some details for this now, and we'll use this for a computation. So don't worry too much about this notation. This notation is going to matter a whole lot in a few chapters. I'm just trying to kind of throw it out there right now so you can kind of start getting used to seeing some of these things. So you don't need to know about this notation for right now, but the computation associated with the average and standard deviation is sort of part of this chapter here. So how might I notate the information in this paragraph right here? Suppose the variety of apples in consideration is normally distributed with an average of 100 grams and a standard deviation of 8 grams. Here I might say something like, let's say the weight of the apples, so I'll say the X values of my apples is normally distributed with an average of 100 grams and a standard deviation of 8 grams. I might say similarly that the variety of oranges, there's my X sub orange, is distributed normally. Oh, I didn't capitalize my N right there. Ooh, and my N right there. I'm going to try and do that so that we kind of remember that distinction. Average of 154, standard deviation of 11. The question that I want to ask you is, what's more unlikely? Finding an apple that weighs 110 grams or finding an orange that weighs 170 grams? And again, it's weird to make this direct comparison because they're not part of the same group. As I'm joking here, we're literally comparing apples and oranges. But the point is, if we know about the distribution of lots of apples and lots of oranges, we can make a judgment as to which of these things seems like a more strange result. You should notice in both of these cases that these are heavier than average, right? This is 10 grams more than average for the apple. This is 16 grams more than average for the orange. Right? So But is that enough? I mean, does that tell me that the orange is the more unlikely thing? And the answer is not really, because I know that the oranges have a larger spread of their data. Their standard deviation is different. The standard deviation is larger. That means that we expect that our bell-shaped curve is going to be a little bit more spread out when we look at the distribution of all those data. It's easier for our oranges to vary from the 154 than it is for our apples to vary from the 100. There is a larger standard deviation. It's more typical for them to spread out a little bit further from their average because the standard deviation is slightly larger. So even though the orange is more grams above average than the apple, that might not actually be that extreme relative to the standard deviation. So what we're going to do is we are not going to just look at the raw amount that it is different from the average. What we want to do is we want to count how many standard deviations away from average are each of these measurements right here. Is that where I got? Okay. So since they're both normally distributed, we can compare these individuals by measuring their z-scores. A z-score is just a fancy name for how many standard deviations away from normal is that. Well, I can do the computation here, right? Now, I know that in this case, I'm going to kind of list some things here. My x sub a, my apple in this case, is 110 grams. My average for the apples, I'll call mu sub a, is 100 grams. And my standard deviation for the apples, hey, there's finally a good standard deviation symbol, is 8 grams. I want to know how many standard deviations away is my apple from the average. So what I'm going to do with those pieces of information that I just wrote down is I'm going to say, well, I know that the distance away that my apple is from the average, I can compute that. I can say, how far is my apple from the average? Well, that's just a subtraction, right? 110 minus 100, that's where I got the 10 grams above average. What I want to do is count how many standard deviations away that is. So I'm going to divide that by the size of our standard deviation. Our computation here then is, we typically denote this as x minus mu over sigma. This says, find how far away you are from the average, and then divide by the standard deviation, and we'll get a count of number of standard deviations that we are away. Here, I'm going to get 10 over 8, which is 5 over 4, and I'm trying to leave the other half, oh man. And this tells me that my z-score here is 1.25. This says that this apple is 1.25 standard deviations above normal. This is a more generic descriptor of how unusual this apple is. Saying that an apple is 10 grams heavier than normal says basically nothing to me, because maybe all apples deviate quite a lot from the average. On the other hand, maybe that you are like a master farmer and maybe you grow apples where like literally every single apple on the whole tree ends up being between 95 and 105 grams. That would have a very low standard deviation. In that case, we would expect the 110 to be an insane apple, right? Here, 1.25, not too crazy. We're above average, but we're 1.25 standard deviations above average. Let's do the same thing for the orange over here so that we can actually make a comparison. In the situation for the orange, I might say that our x sub orange here, the x value, the weight of the orange, we said, I don't remember my values here, the weight of the orange was 170. The average weight of the oranges is 154. And the standard deviation of orange size, those vary a little bit more than the apples did. They have a slightly larger standard deviation of 11 grams. And by the way, all these do get these units right here. That's grams, grams, grams. You should notice that since this is grams minus grams, this is 10 grams divided by 8 grams, the units canceled. Z-scores are unitless. It's just a count of number of standard deviations. So all the numbers on the screen right now have units of grams, except for this one. And that's because we divided 10 grams by 8 grams to just get to the number 1.25. The units of grams divided by grams canceled. So for our computation over here again, these are grams, grams, grams. We can do the same thing. We measure that 170 minus 154 is going to be that 16 units away. We can divide that by the 11 grams. That represents one standard deviation. Can't quite do this one in my head right here. So 16 divided by 11. And I'm getting 1.5 or 1.4545. So I'll just 1.45 5. And this would be our z-score associated with that one orange. This orange that we picked, this orange that's 170 grams, it is 1.45 standard deviations above normal. So what I can finally conclude now is that at the beginning, I can't just tell you which of these fruits is more unlikely than the other. I needed to know information about how these fruits are typically distributed to know, is that a weird fruit or not? Like it depends on how typically spread out these things are. I want to point out real quick that if this number 11 were just as big as, let's see, 16 divided by 12 would keep us still above. 16 divided by 13 though? Yeah, so notice here, by the way, I'm just going to say this. If oranges actually had our standard deviation being 13, then 170 minus 154 over 13, that would be giving us 1.23. So notice here, if instead we had a slightly larger standard deviation on those oranges, then now you should see that the z-score for the oranges is smaller than the z-score for the apples, suggesting this says since there's more variability that typically does occur with those oranges, it's not that weird anymore. It's less weird for us to have seen this 170 gram orange right here. So with just a slightly bigger standard deviation, we now would say that the oranges are less unusual. This orange is less unusual than the apple. It is not as far away from its average in count of standard deviations, right? So it matters that we know how our data are spread out, right? And again, we don't want to just make an absolute measurement like the 10 grams and the 16 grams. It matters that we say that we incorporate into this how typically spread out are the data as well. So let me just kind of conclude this by saying here, the orange is now uh, more common as compared to more unusual, right? Or the apple is now the more unusual one in the second scenario right here. Right, so computing z-scores is pretty easy. It's always going to be based on this computation right here. Let me go back and highlight this since it was sort of falling off my screen over here. A z-score is how many standard deviations away from normal, or excuse me, away from average, a single observation is. So in this, remember, our x is our individual observation. Our mu is our average, population average, and our sigma is our standard deviation. So if we know the average and standard deviation of a data set, it helps to know that it is a symmetric data set, normally distributed is very common out there. Then we can always measure how unusual a single observation is going to be. We're going to look a lot more at z-scores later, but it is good for us at least right now to be able to compute a z-score across two different things and determine which one of those two things is more of an unlikely event. This is getting into our probability discussion. I mean, we're going to start probability next week, and this is now making probability statements. The probability that we would see in just the situation on the screen right now, the probability of seeing a 110 gram apple seems to be a larger probability than a 170 gram orange. The 170 gram orange was more unusual. It's further from its average right here. So this is the more unusual thing to see. This would be the more usual relative to the two right there. All right. So computing z-scores is a really good way for us to compare two things that aren't from the same data set. As long as we know information about the data set, particularly its shape, center, and spread, then we can make comparisons across between two observations that don't even belong to the same category of object. Because now I can do things like say, what's more uncommon? A bald eagle having a wingspan of 7 feet or my child taking 9 poops in a day? Like now we can actually compare those directly if I knew the distributions associated with each of those populations. If I took every single measurement of all of my son's diapers and measured all the bald eagles, then I could actually make a legitimate judgment about that, and I would do that using a z-score comparison. All right. So let's just go ahead and look at a cool thing on the internet, and we'll call it a day here. Um, our special example of intentionally misleading data. And when I say intentionally misleading data, I just kind of like prep you for what we're going to see right here. What we're going to see here, this is Anscombe's quartet. So the dude's name was I don't know, his last name is Anscombe. And quartet meaning four things, right? A quartet, we usually think like four people in a music group or something like that. This is going to be four data sets. And what his frustration was that he was frustrated that there are lots of people saying things to him like, just go ahead and compute your statistics for this stuff. People saying that, oh, you're not going to get a good idea of your data from looking at a graph. You need to compute some statistics. And he's like, you're wrong, and I'm going to prove to you that you're wrong. And so the little lesson that is contained within Anscombe's quartet. Anscombe's quartet is not real data. It is just fake data that was made to just prove a point to people that it does matter that you truly look at raw data, that you truly look at the shape of your distributions before you attempt to ever make any conclusions about the data that you're actually looking at. So Anscombe's quartet, let's pop over to the internet here and take a peek. So I'm just going to Google for it here. I'm just going to do wiki, and I already looked at it earlier, so there it is, wiki Anscombe's quartet. Let me zoom in here so you guys can see. There we go. I'm just this. By the way, this is how I Google lots of things, is just sticking wiki in front of it, because it usually takes me to a place where people are actually trying to like kind of formally give me information about it. This is a thing I might recommend that you do for lots of like school related stuff. If you're ever looking for like help with a class and you're like, crap, I can't figure out this thing about standard deviation, do like wiki standard deviation. You'll at least not get sent to some crappy site. You'll at least get sent to Wikipedia, which is pretty reliable these days for especially things like this. So go in here. I'm going to go to Anscombe's quartet. There's a Wikipedia page for it. And so here's the deal. Anscombe's quartet is technically these four data sets. You can see that they are marked. Let me just zoom in a little. Oh, it unzoomed me. Oop, that was too much. Anscombe's quartet. So you can see it's just a list of data points here. Data set 1 has an X column and a Y column. All of them have an X column and a Y column. And you should notice that, I don't know, like I'm guessing if you, like me, are looking at this, you're like, I don't know, there's some numbers on my screen, whatever. My question to you that we're really asking here is like, how are these data sets related to each other? And I'm kind of noticing some funny things. Like, for example, look at this X column right here. 888888888 88888. That's a weird column right there. It doesn't look to me like this stuff is doing the same things as the other stuff is doing out there. The very interesting thing about these four data sets is that all four of these data sets have an X average of 9 exactly. All four of the data sets have a variance of X values of exactly 11. And remember, you can take the square root of that to get the standard deviation. The average of their Y values are all essentially exactly the same. You didn't get it to work out quite the exact right, but they're all about 7.5. The sample variance for the Y values are all essentially exactly the same. We're going to talk about correlation, linear regression, and coefficient of determination. That'll be like our last unit of the semester. It's last because it's easy, and I want to end with something soft. And so this will be our nice, easy wrap up to the semester right here. But the important thing is to look at these graphs. These are the four data sets that are being described here. These look nothing alike. It is hopefully incredibly obvious to you that these are not describing data that has been drawn from the same population. It's not like this is just four samples from the same population. These are wildly different from each other. But in all four of these cases, the average X value of the dots is the same. The average Y value of the dots is the same. The standard deviation of the X values is the same. The standard deviation of the Y values is the same. The line of best fit, the line that is closest to all possible data points, the minimum distance away from all the data points, is exactly the same equation of line. It's 3x plus 5 in all four cases. This is ridiculous. And even the, not just where is this line of best fit located, but the actual average distance from the line itself is also equal in all four of these cases. This is crazy, right? So this is like the best thing that's ever happened to teachers teaching statistics is getting to show this like little grouping of four plots right here. The statistics that we would compute for all four of these data sets are identical, but it is hopefully incredibly obvious to you that the data that we have drawn from have nothing to do with each other. There is no similarities between these data sets here. And so the lesson to be learned here is just because you know the average and the standard deviation and even a line of best fit that might relate the variables in your data sets, that does not really mean that you know what you're talking about. There's lots of possibilities that could still be going on out there. And so this is just to say, like, there could not be any argument with the statement, you have to just look at your data whenever you're doing any sort of statistics stuff. If you don't graph it and see what it looks like, if you don't kind of plot some things, make a histogram, something like that, then it is not necessarily realistic that you can make a claim that you know what your data is going to look like. I would like to make one statement about this, though, before I kind of walk away right here. You should notice that one of the things that wasn't discussed in this was median. This is about average standard deviation and relationship between X and Y. The median for these would be different. I can tell that the median of this data set is 8. I don't even need to do any computation. There's a whole mess of 8s. More than half the data points are 8, then the median's 8. It's got to be the case. I can tell over here that the medians for these, wait a minute, are actually the medians the same? I don't think the median will be, well, we can just do it here, right? Couldn't I just chop off some of these? Is it going to let me write on this? Let's see here. Uh, Come on, let me write on this. It's not going to let me write on it. Um, okay, maybe actually the medians are the same. But anyway, the point is that's drawing attention away from the right thing. Just looking at the numbers, just looking at the statistics, that's never enough for you to claim that you fully know what you're talking about. And so, as I said today, just knowing the center and spread isn't quite enough. We want to know shape, center, and spread so that we can make meaningful interpretations about the data set. Here, the center and the spread are identical across all four data sets, but the shapes are wildly different from each other, and therefore the computations and interpretations that would be associated with these things should wildly differ from each other, even though they all experience the same average and standard deviation and relationships between X and Y. So this is just sort of like the perfect educational tool as a warning to say, don't go overstating what you think you know. Don't just think that knowing the average and standard deviation is good enough. It matters that we identify the shape of the distribution of the data as well, so that we can fully say that we really understand how to make interpretations about that data. All right. I think that's all I've got here for us today for our wrap up for chapter 2 stuff here. As I said, I am super excited because chapter 3 is I wish that I could just teach an entire class on probability. That's kind of one of my like long-term teaching desires is to have an entire semester's course just on probability. There's so many interesting things to compute, so many things that are not what you think they are. Probability can get tricky, but it's also great because everybody has really deep intuition for it. We've all rolled dice, we've all flipped coins, we've all experienced unlikely events in our life. And so we're going to talk about all those things associated with probability next week in chapter 3. So you guys should have your My Open Math homework available. You should have a by hand homework available. There's not a comprehension quiz in Canvas this week associated with these videos. I'll probably do that next week. I think next week will lend itself better to doing that again. I really kind of felt like this week, on the one hand, I kind of fell behind because I was gone for the weekend, but on the other hand, a lot of this week was about just this computation of these statistics that we are going to use heavily over the rest of the semester. And so I kind of ended up feeling like my Open Math quiz question, or sorry, my Canvas quiz questions would have ended up being the same as the My Open Math questions anyway. So that was sort of my justification. I'm still planning on doing these comprehension quizzes, so do look for that next week, but there isn't one for this week. So that's wrapping it up for me here today. I will see you guys on Monday at 10:30 if you're here for the live one for our beginnings of chapter 3, and we will